Did you know that we actually slowed down Earth's rotation? This isn't an exaggerated line from a documentary. It's a measurable fact, confirmed by precise scientific observation. When China's Three Gorges Dam is completely full, it holds about 40 billion cubic meters of water in a single enormous reservoir. That massive weight slightly redistributes Earth's mass, increases the planet's moments of inertia, and as a result, lengthens the duration of a day by roughly 0.06 microseconds every 24 hours. At the same time, Earth's rotational axis shifts by about 2 centimeters. You can't see it with the naked eye, but atomic clocks and high-precision geodetic instruments detect it clearly. So how does this happen technically? It all comes down to the movement of water. When the dam fills, the water that would normally be spread along the river gathers into one huge reservoir. And part of that mass ends up in a slightly different position relative to the Earth's rotation axis. This is the basic idea behind what we call the moment of inertia in physics. The easiest way to understand it is to imagine a figure skating. As the skater spins, an invisible axis runs from their head to their feet. When they extend their arms outward, their mass moves away from that axis. Their moment of inertia increases and they slow down. But when they pull their arms inward, their mass moves closer to the axis. Their moment of inertia decreases and they spin much faster. Earth follows the same physics. When the distribution of mass shifts, so does the planet's rotational speed. A dam like the Three Gorges relocates tens of billions of tons of water, increasing Earth's moment of inertia by a tiny amount, just enough to lengthen the day in a measurable way. And because this mass shift isn't symmetrical, the imaginary line defining Earth's rotational axis also shifts by millimeters to centimeters towards a new equilibrium axis. In other words, this reservoir reshapes not only the river's flow, but also the rotational geometry of the entire planet. To understand the Three Gorges Dam, you need to look at the map. The Yangtze River stretches across China from west to east, shaping the country's history for thousands of years through its floods, fertile plains, and trade routes. The name Three Gorges comes from the three deep valleys where the river narrows between towering cliffs. The dam sits right in the middle of these gorges, a geologically strong yet sensitive point. The concept of a dam here dates back to the early 20th century, but technological limitations and political debates kept it on hold for decades. When China entered a period of rapid industrialization, the Yangtze's potential came back into focus. And by the 1990s, the country finally reached a point where it could say, "We can build this." When construction began in 1994, the Yangtze Valley became one of the largest engineering sites in the world. The river carries tens of thousands of cubic meters of water every second. So it flows couldn't simply be stopped. It had to be redirected. Engineers built temporary coffer dams and massive diversion tunnels to reroute part of the river, exposing the area where the dam's foundation would be laid. Deep excavations were carried out into the riverbed, and the dam was designed not just as a vertical wall, but as a colossal concrete block anchored into the surrounding rock. During the busiest phases, construction continued around the clock. By day, trucks, cranes, and concrete pumps built the site. By night, floodlights turned the gorge as bright as daylight. More than 20 million cubic meters of concrete were poured to prevent cracking in such a massive structure. Cooling pipes were embedded within the dam, circulating the water to control internal temperature. What looks like a simple concrete wall from the outside is actually a complex system. Water circulates through it. Heat is regulated and sensors constantly monitor its structural integrity. Because the Yangtze is also a vital shipping corridor, it was essential to maintain uninterrupted river traffic. The solution was twofold: a 5-stage ship lock system and a gigantic ship lift. The lock system, similar to the Panama Canal, raises ships step by step by filling and draining water chambers. The ship lift, however, can lift vessels weighing up to 3,000 tons, more than 100 meters in a single motion. Ships enter a huge steel chamber and the entire chamber is lifted vertically, like a freight elevator. It is one of the largest lifting systems ever built, transforming river transportation from purely horizontal terrain into one that also moves vertically. When the reservoir began to fill, not only the water level changed, the landscape changed. The reservoir extended nearly 600 kilometers inland, redefining the shape of the valley. When the water level reached 175 meters, hundreds of settlements along the river were submerged. Around 1.4 million people were relocated to newly built towns, a population movement comparable to relocating the entire city of Philadelphia. Higher and safer areas in places like Fuling, Guangzhou, and Badong became new population centers. Villages, ports, roads, and bridges disappeared underwater as the shoreline was redrawn. At this scale, the project was no longer simply a dam. It was the transformation of an entire region. The weight of the reservoir also affected the region's geology. The water pushed down on the valley's rock layers, increasing pressure on the slopes. After 2003, hundreds of new landslides were recorded. In some areas, millions of cubic meters of soil and rock collapsed into the reservoir. Scientists note that the constant filling and draining of the reservoir changes pressure on the ground, increasing the frequency of small earthquakes. Every fluctuation in water level adds stress that can trigger minor tremors. The ecosystem changed just as dramatically. Before the dam, the Yangtze carried massive amounts of sediment each year, nourishing its delta and enriching farmlands. After the dam was built, sediment flow dropped sharply, causing the delta to shrink, coastal erosion to increase, and saltwater intrusion problems in some farming regions. Migration routes for fish were blocked, breeding grounds shifted, and populations of several species fell rapidly. China's iconic river dolphin, the baiji, was declared functionally extinct despite conservation efforts. Despite these impacts, the Three Gorges Dam also brings enormous benefits. With a capacity of 22.5 gigawatts, it is the largest hydroelectric plant on the Earth, equivalent to the output of about 50 nuclear reactors running simultaneously. It produces more than 100 terawatt hours of electricity annually, enough to power more than 80 million homes, and prevents the burning of millions of tons of coal each year, significantly reducing carbon emissions. It also helps control the Yangtze's historically devastating floods, making water levels more stable and predictable. In every sense, engineering, geophysical, and socioeconomic, the Three Gorges Dam has become a global heavyweight. But if one dam can have such an impact, what about the thousands of dams around the world? During the 20th century, humanity entered what could be almost called a dam era. Today, there are more than 50,000 dams worldwide, about 7,000 of which are considered major dams. Their reservoirs hold more than 10,000 cubic kilometers of water. Normally, much of this water would reach the oceans. Now, it is stored in lands for decades. Mechanically speaking, what we see at the Three Gorges Dam repeats on a global scale. Massive amounts of water are constantly being moved and stored across continents, altering Earth's mass distribution in subtle but continuous ways. According to GRACE satellite measurements, large dams built between 1835 and 2011 shifted Earth's rotational pole by about 1.1 meters. This movement aligns with the geographical pattern of dam construction. In the 19th century and early 20th centuries, dams were concentrated in North America and Europe, so the pole drifted in a particular direction. After the 1950s, as dam construction expanded in Asia and Africa, the direction of this drift gradually changed. In other words, Earth's polar motion carries a faint but measurable signature of where humanity stores its water. Dams also influence sea level. Because some of the water that should reach the oceans is instead stored in reservoirs, global sea level during the 20th century was 21 to 23 millimeters lower than it would otherwise have been, about 1/4 of the century's total rise. This doesn't stop sea level rise, but it noticeably slows it. However the effect of a rise, some coastlines feel the impact strongly. others barely at all. Water management extends beyond dams. Excessive groundwater extraction, especially for irrigation, also alters Earth's mass distribution. Studies covering the 1990s to the 2010s show that groundwater depletion shifted Earth's rotational axis by about 80 centimeters. In just a few decades, this change represents a significant portion of the axis shift caused by dams over 2 centuries. The mechanism is the same. Groundwater is pumped out, transported elsewhere, evaporates into the atmosphere, and returns as a precipitation to different latitudes, reshaping mass distribution. On top of all of this comes an even larger factor: melting ice sheets. As global temperatures rise, Greenland and Antarctica are rapidly losing ice. When this ice melts and moves from the poles to lower latitude, it affects Earth's mass balance far more than dams ever could. Some models estimate that by the end of the century, ice sheet melts may shift Earth's rotational axis by 20 to 30 meters, tens of times greater than the combined effect of dams and groundwater use. Ultimately, a picture is clear. Humanity is no longer just a species that builds cities, roads, and bridges. We redirect rivers, store waters in giant reservoirs, pump groundwater, and accelerate the melting of glaciers. And together, these actions leave a measurable imprint on Earth's rotation, its axis, and its water cycle. The Three Gorges Dam is one of the most visible examples of this phenomenon. On its own, it can lengthen the day by microseconds and shift the axis by centimeters. Combined with thousands of dams and water projects worldwide, the effect extends from polar motion to sea level changes. We now understand that when we build a wall across a river, we're not just altering the water's path, we're subtly but measurably rewriting the behavior of the planet itself.